Welcome to the third lecture, the Enhanced Entity Relationship Model. Let's discuss this in a little bit more depth so you understand what is entity, what is relationship, and how we can use that to model and find our understanding in more depth with the database that we are dealing with. We will be learning the terms that we are going to discuss: one-to-one, one-to-many, many-to-one, many-to-many, as we have been discussing in earlier lectures. Understand the supertype, subtype relationships, use specializations and generalization techniques, specify completeness and disjointness constraints, develop supertype, subtype hierarchies for business situations, develop entity clusters, explain universal packaged data model, describe special features of data modeling project using packaged data model. So I would suggest you to read all these in your prescribed text. And any questions once this lecture is finished, you are most welcome to discuss those with me. Supertype and subtype. The ER or enhanced ER model extends original ER model with new modeling constructs. Subtype is a subgrouping of the entities in N entity type that has attributes distinct from those in other subgroupings. We will be discussing these in quite depth. Supertype is a generic type or generic entity type that has a relationship with one or more subtypes. Attribute inheritance comes in terms of subtype entities inherit values of all attributes and relationships of the supertype, whereas an instance of a subtype is also an instance of the supertype. Let's look into this in a little bit more depth in the upcoming slides. First, let's consider a university scenario. In a simple ER model, you might have entities like student and course, as we discussed earlier. However, in an EER or enhanced entity relationship model, you can represent more complex relationships. For instance, you can have a takes relationship between student and the course, which is many to many, meaning each student can take multiple courses and each course can be taken by multiple students. Additionally, you can have attributes specific to the relationship like grade, which depends on both the student and the course. Second, consider business with employees and the projects. In EER model, you can represent a hierarchy among employees using a superclass and subclass concept. Employee is a superclass with attributes like employee ID and name. Subclasses could be manager and engineer, each with their own specific attributes like department for managers and specialization for engineers. This allows for more detailed and accurate representation of the real-world scenario. Third, let's look at a library system. Here you might have the entities like book and member. In an EER model, you can represent a multi-level categorization of books using the category, entity, and self-referencing relationship. A book can belong to a category. The category can have subcategories which are also categories themselves. For example, science fiction could have subcategory of fiction. This is another example of EER models can represent complex real-world relationships more effectively than simple EER models. Hopefully this has given you a little bit in-depth understanding. The idea of supertypes and subtypes and inheritance, which are central to the EER model, are also the key concepts in object-oriented software design and programming. If you ever use an object-oriented programming language like Java or C++, you will encounter the concept of classes, which are similar to types. These classes are arranged in hierarchies, which enable inheritance. The difference between object-oriented programming and EER, supertypes and subtypes or subtypes, is that the object-oriented programming, there is also the concept of behavior. Object not only have attributes which can be inherited, but also have methods which can implement in active behaviors comprehension way. So this is only one possible notation for EER. In other figures, we will see Microsoft Visio notation, which is similar but is not identical. However, I suggest you to use standard PowerPoint slide deck, and you can actually create this sort of figure easily, where supertypes have several subtypes, and these subtypes can be specialized versions. Let's say if you have history, you can have historical fiction, you can have actual history, or you can have someone's research that they have conducted on history, which they have combined several people's work in terms of specialization aspect. These are the EER notations. Basic notation for supertype and subtype notations. The primary key, or PK, is an identifier of a shared attribute, and then we have that primary key can roll in as a foreign key in the subtype 1, subtype 2, and the list can go on. These are the Microsoft Visio notations. So it makes sense to model supertypes and subtypes if certain attributes or relationships apply only to a subset of the total entity types, whereas others are shared across the entire entity type. In this case, all employees have names, addresses, and hire dates, but only hourly employees have hourly rates. Only salaried employees have salaries and stock options, and only consultants have contract numbers and billing rates. If we simply had an employee entity, then these special purpose attributes would be irrelevant for many of the employees. So relationships at the supertype level indicate that all subtypes will participate in the relationship. The instance of a subtype may participate in a relationship unique to that subtype. In this situation, the relationship is shown at the subtype level. Let's look into that with an example or two. In the enhanced entity relationship model, relationships are at the supertype level, involves entities that have a generalization specialization hierarchy, as we discussed earlier. This means there is a supertype entity with general attributes and one or more subtype entities with more specific attributes. Relationships can be established at the supertype level, and these relationships are inherited by the subtypes. Let's look at two examples to illustrate this concept. First, consider a university setting where the supertype entity called person, the person entity, has general attributes like person ID and name. There are two subtypes, student and faculty. The student subtype has specific attributes like major and the year, while the faculty subtype has attributes like department and the rank. A relationship at the supertype level can be person participates in event. This relationship is inherited by both student and faculty. For instance, both students and faculty member can participate in university events like seminars or workshops. This relationship at the supertype level allows for a unified way to handle participation in events, regardless of whether the participant is the student or a faculty member. Second, let's look at a healthcare system with a supertype entity called employee. The employee entity has general attributes like employee ID and name. There are several subtypes: doctor, nurse, and administrator. The doctor subtype has specific attributes like specialty and a license number. The nurse subtype has attributes like certification and shift, and the administrator subtype has attributes like department and role. A relationship at the supertype level could be employee works in a department. The relationship is inherited by all subtypes. For example, doctors, nurses, and administrators all work in specific departments within the healthcare facility. This relationship at the supertype level provides a consistent way to manage the assignment of employees and to departments, regardless of their specific roles within the healthcare system. These examples demonstrate how relationship at supertype and subtype level can be used to model common interactions that apply with the features, behaviors, and the attributes of the objects which we are dealing with within our database to multiple specialized entities, promoting a more organized and flexible database design. So that's the significance of the relationships and subtypes. So this is a good example of the distinction between shared attributes relationships and specialized attributes relationships. So it makes sense to break patients into two subtypes, as I just mentioned. This is the depiction of my second example that I shared with you, where a person can be a patient, a person can be a physician can be a patient and come back to the system to be treated. There can be outpatients, resident patients, and the bed ID if the bed is available, and this is a little bigger clinical system or a hospital. So generalization and specialization. The generalization is the process of defining more general entity type from a set of more specialized entity types bottom up, whereas specialization is the process of defining one or more subtypes of the supertypes and forming supertype subtype relationship top down. Let's look into that in a little bit more depth. Let us consider a manufacturing facility to illustrate the concepts of generalization bottom up and specialization top down. In a manufacturing facility, you might initially have two separate entities, robot and machine. The robot entity has attributes like robot ID, model, and programming language, while the machine entity has attributes like machine ID, type, and power source. As you analyze your data model, you realize that both robots and machines share some common attributes like ID, manufacturer, and purchase date. To reduce redundancy and better organize your data, you create a supertype entity called equipment. With these common attributes, the robot and machine entities then become subtypes of equipment. This process is called generalization because you are creating a more general entity or in terms of equipment from two specific entities, robot and machine. Whereas, what is specialization? Let's take an example. Let's consider an employee entity in the same manufacturing facility. The employee entity has attributes like employee ID, name, and hire date. As your manufacturing facility grows, you realize that you need to track more specific information about different types of employees. You decide to create subtypes of employee to represent different roles: engineer, technician, and manager. The engineer subtype has specific attributes like engineering discipline and license number, and technician subtype has attributes like specialization and certification, and manager subtype has attributes like department and management level. This process is called specialization because you are creating more specific entities, engineer, technician, and manager, from a general entity, employee. This is also called persona or personification. These examples demonstrate how generalization and specialization can be used in a manufacturing facility to create more organized and efficient data models. Generalization helps to reduce redundancy by combining common attributes into a supertype entity, while specialization allows for more detailed and specialized representation of different types of entities. Hopefully, this has given you a more understanding of generalization and specialization. So sometimes during a conceptual modeling process, we begin to recognize common themes among several entity types. For instance, they may all share many of the same attributes as mentioned earlier, such as in this example here, cars, trucks, and motorcycles all have prices, engine displacements, and vehicle makes and models. So when this happens, we can create a supertype and place the shared attribute in the supertype entity. This process is called generalization. The specialized attribute go into subtype entities. In the case of the motorcycle, there is no unique attribute, so there is no need for a specific motorcycle entity. Actually, it may be useful to have an indication that a vehicle is in fact a motorcycle. Later, we will discuss the concept of subtype discriminator, which is a special attribute at the supertype level and that identifies a specific subtype. Sometimes during a conceptual modeling process, we discover that certain attributes or relationships apply only to a subset of the entities in a given entity type. In this example, we have a manufacturing firm that may manufacture some of its own parts and purchase others. If the part is manufactured by the firm itself, it has a routing number. But if purchased, it does not. If purchased, it comes from a supplier, but if manufactured, it does not. Note the representation of supplier as a composite multi-valued attribute in this diagram. When we find a situation like this, it makes sense to do specialization. In this case, we created two subtypes of part, one or for manufactured parts and one for purchased parts. All parts have part numbers, descriptions, locations, and quantity, but only manufactured parts have routing numbers and only purchased parts have suppliers. Note that unlike the previous slide, the concept of supplier is now represented as a separate entity and the associative entity represents M to N relationship between purchased parts and supplier, with unit price being an attribute of the associative entity. This provides information that was not explicit in the previous figure. A multi-valued attribute does not explicitly describe M to N relationship. It could also convey a 1 to N relationship, but when you represent the supplier as a separate entity, you can explicitly show for cardinality of relationship. For example, of a multi-valued attribute that implies a 1 to N relationship refers to in the figure 2.19 from chapter 2. Here we have time stamps of price history changes. For a given product, there may be many price history items, but each price history item belongs to only one product. That is different from what we have here with parts and suppliers, where the part can have many suppliers and supplier could supply many parts. So many to many relationship kicks in automatically here. So there are two types of constraints in supertype and subtype relationship. One is called completeness constraint and indicates whether there must be an explicit subtype for each possible instance of the supertype. The other is called a disjointness constraints, which indicates whether the particular instance of supertype could also be more than one supertype. So let's look into that in more depth. Constraints in supertype-subtype relationships matter because they ensure data integrity, consistency, and accuracy within a database. They help to enforce rules and maintain the logical structure of the data model. Let us discuss the constraints in a little bit more depth with few examples. The total participant constraint is number one that we'll pick here. The total participant constraint ensures that every instance of the supertype must also be an instance of at least one subtype. This constraint is crucial when you want to guarantee that every general entity has a specific role or category. In a university database, consider the supertype person with subtypes students, faculty, and staff. A total participation constraint ensures that every person in the database is either a student, or a faculty member, or a staff member. Without this constraint, you might end up with person records that are not categorized, leading to incomplete or ambiguous data. This constraint helps maintain a clear and organized classification of individuals within the university. So, there are two types of constraints in supertype and subtype relationships. One is called completeness constraint and indicator whether there must be an explicit subtype of each possible instance of the subtype. The other is called disjoint constraint, which indicates whether a particular instance of a supertype could also be more than one of two subtypes. The disjoint constraints ensure that an instance of the supertype can belong to a most one type. This constraint is essential when a supertype are mutually exclusive categories. In the healthcare database, consider a supertype employee with subtype doctor, nurse, and administrator. The disjointness constraint ensures that an employee cannot be both a doctor and a nurse, or a nurse and an administrator. At the same time, without this constraint, there could be confusion about an employee's role and responsibilities. This constraint helps maintain the logical separation of different job roles within the healthcare facility. So hopefully this has given you some understanding that why constraints in supertype and subtype relationship even matter. So in this case, a patient must either be an outpatient or a resident patient. There is no other possibility. This particular completeness constraint is called total specialization and is represented by double lines coming down from the supertype entity type. We already saw the example from earlier. This is partial specialization because some vehicles are motorcycles, which is not explicitly represented as a subtype entity. The question is, going back to figure 3.5, do you think the division of part into manufactured versus purchased parts implies total specialization or partial specialization? And obviously, I would like you to think about it. Once the lecture is finished, I would like you to answer that and figure out if you understood what exactly the figure 3.6 is giving in terms of an understanding. Constraints in supertype subtype relationships. Disjoint constraints has disjoint rule and overlap rule. Whether an instance of a supertype may simultaneously be a member of two or more subtypes. You can be a professor. Simultaneously, you can attend the same university to have another certification in your curriculum, and that makes you a student as well. The disjoint rule, an instance of the supertype can only be one of the subtypes. Overlap is an instance of the supertype could be more than one of the subtypes, as I just shared with you. Here we see a disjoint, not overlap rule regarding patients. A patient can be both a resident and an outpatient. Must be one or the other. At least one of the same time. At least not at the same time. Of course, it is possible for a patient to be a resident for a period of time and then change to an outpatient or vice versa, but the patient cannot be both simultaneously. Here is an overlap rule. Some kind of parts could be manufactured in-house and also purchased from external suppliers. Note that total specialization rule, which we discussed earlier, is applicable here. So subtype discriminator, an attribute of the supertype whose values determine the target subtypes. The disjoint a simple attribute with alternative values to indicate the possible subtypes. Overlapping a composite attribute whose subparts pertain to different subtypes, each subpart contains a Boolean value to indicate whether or not the instance belongs to the associated subtype. So hopefully this is giving you some decent idea. We will also be looking at covering constraint. The covering constraint is a combination of total participation and disjointness constraints. It ensures that every instance of the supertype belongs to exactly one subtype. This constraint is useful when you want to guarantee that every general entity has a unique and specific role or category. Example here can be in a manufacturing facility database. Consider the supertype equipment with subtypes robot, machine, and vehicle. A covering constraint ensures that every piece of equipment is either a robot, a machine, or a vehicle, and that no equipment can belong to more than one category. Without this constraint, you might have equipment that is not properly categorized or is categorized in multiple conflicting ways. This constraint helps maintain a clear and unambiguous classification of equipment within the manufacturing facility. These examples demonstrate why constraints in supertype-subtype relationship matter. They help to enforce data integrity, prevent ambiguity, and maintain logical structure of the data model. By using these constraints, you can ensure that your database is accurate, consistent, and well organized. Constraints can also be partial. Not every instance of the supertype needs to belong to a subtype or overlapping. An instance of the supertype can belong to multiple subtypes depending on the specific requirements of the data model. However, the total participation disjointness and covering constraints are most common and illustrate the importance of the constraints in supertype and subtype relationships. So when you are going to go through your prescribed text, that will allow you to understand all these constraints and types and relationships in more depth. So here for the disjoint rule, we have employee type as a subtype discriminator, and it can have three possible values, one of each subtype. Going back to figure 3.7, what would be a possible subtype discriminator and what would its value be? Think about it. So note the equipment for a composite subtype discriminator here. So there are three possible ways. Manufactured is equal to Y and purchase is equal to Y. Manufactured is equal to Y and purchase is not equal to, technically is N. Manufactured, it's N, and purchase is N. So note that it is impossible for this scenario to occur. Manufactured is N and purchase is N. It means neither manufactured nor purchased. Then what happens? Why is this not possible? Think about that. Because of the total specialization rule. At least one of these have to be a Y, means yes. Either it is manufactured or purchased. Means if you are having windows replaced in your house, you can use one of your current window because it's in a great shape, and the second window which is a little distorted, you can buy another one. So you have an in-house window that you are getting refurbished, and then you're changing altogether a brand new window. Supertype and subtype hierarchies can be as deep as we want them to be. Here we see that faculty is a type of employee, which is a type of person. Question: note that there is a person must be either an employee, alumnus, or student. Is it possible for a person to be both an employee and a student? Why and why not? The answer is yes, because of the overlap rule. Can you envision what the person's subtype discriminator would be. Answer, it has to be composite attribute. Another question comes here. Is it possible for an employer to be something other than faculty or staff? Why or why not? Yes, because of partial specialization. Question. Another question comes, is it possible for an employee to be both faculty and staff? The answer is no, because of disjoint, not overlap, under employee. Another question can be, is it possible for staff member to also be a graduate student? Yes, because of the overlap rule under the person. Another question, is it possible for someone to have more than one degree from this university? Yes, because a degree is multi-valued attribute. Entity clusters. Let's look into this with few examples. Entity clusters are a concept in database design where multiple entities are grouped together based on some common characteristics or relationship. These clusters help to organize and manage related entities more effectively, making the data model more understandable and maintainable. Let's discuss few of these examples to understand it in more depth. Customer interaction cluster is our first example. In the customer relationship management or CRM system, several entities can be grouped into a customer interaction cluster. These entities are related to each other through their involvement in customer interactions. Entities in the cluster would be customer, sales order, support ticket, and feedback. Customers' features are customer ID, name, contact information. Sales order has order ID, order placed by who, customer ID, order date, and total amount. Support ticket, a ticket ID. Ticket might be initiated by a customer, so customer ID, issue description, and status. The feedback would have feedback ID, customer ID, rating, and comments. This is an entity cluster for a given scenario in CRM or customer relationship management. What are the relationships? A customer can place multiple sales orders. A customer can create multiple support tickets. A customer can provide multiple feedback entries. Grouping these entities into a customer interaction cluster helps to manage all customer related activity centrally, making it easier to track and analyze customer interaction and provide better customer service. Next example is product management cluster. In an e-commerce platform, several entities can be grouped into a product management cluster. These entities are related to each other through their involvement in managing products. Entities in the cluster are product, category, inventory, and supplier. Product has features product ID, name, description, price. Category has features category ID, name, and description. Inventory has inventory ID, product ID, quantity, and location. Supplier has supplier ID, name, and contact information. What are the relationships here? A product belongs to a category. A product has an associated inventory record. A product is supplied by a supplier. Grouping these entities into a product management cluster helps us streamlining the product related operations such as categorizing products, managing inventory, and tracking suppliers. This cluster promotes efficient product management and improves data organization. Last not the least, we can also look at project management cluster. In the project management system, Several entities can be grouped into a project management cluster. These entities are related to each other through their involvement in managing projects. Entities in the cluster can be project, task, team member, and resource. A project has project ID as feature, name, start date, end date, and a budget. A task has task ID, which belongs to a certain project, so project ID, description of the task, due date, and status. Task complete, task not complete, task in progress. Team member has member ID, name, role, skills. Resource has resource ID, type, availability. Relationships are project consists of multiple tasks. A project is assigned to multiple team members. A project requires multiple resources. Grouping these entities into a project management cluster helps to centralize project related activities such as tracking tasks, assigning team members, and allocating resources. This cluster facilitates better project planning, execution, and monitoring, leading to improved project management efficiency. These examples illustrate how entity clusters can be used to organize and manage related entities more effectively by grouping entities based on their common characteristics or relationships. Entity clusters promote better data organization, improve data management, efficiency, and enhance the overall understandability and maintainability of the data model. Hopefully, this has given you an in-depth understanding why entity clusters matter. So here we see 22 entities. That is a lot and can be difficult to read, make sense of at an aggregate summary level. So possible entity clusters using Microsoft Visio. You can do the same thing in PowerPoint. Related groups of entities could become clusters. So this is an example of entity clustering for Pine Valley Furniture Company that we were discussing. It has selling unit, a customer, a product line in terms of item that belongs to a product line. It can be bedroom furniture, it can be drawing room furniture, it can be dining room furniture, it can be parlor furniture, and all that jazz. It can be bookcases. Item sales has order and order line. The material, whether it's wood, it's titanium, or it's something else, iron. And then we see employee has a skill level, management employee, union employee. Manufacturing has been done in the Pine Valley Furniture Company, or they are purchasing that, as I just discussed that earlier. So enhanced entity relationship diagram for entity clusters using Microsoft Visio, you can do that. You can use it in standard PowerPoint as well. It is more readable. So the entity clustering for Pine Valley Furniture Company has selling out, relates to, does business in, relates to a customer. Customer is purchasing, that's why a selling unit is an entity that is described here. Obviously, every unit has a material that it is manufactured with. The material uses item. So item technically is the one that is built by material, and item is sold. Item is also produced in or manufactured in the company. So you can imagine the entity cluster diagram is to be a bird's eye view model. The modeler can then drill down to see detailed views of individual clusters. So here in work center, someone works in, and that someone can be union employee or can be management employee. the employee has a skill level. So let's say, for example, if I am an employee of Capital Technology University, my skill is teaching. Also, my skill is being PhD advisor. So these are two different skills I use while I work for Capital Technology University, and the rest is history. You can do the same thing, by the way. So package data models, let's look into that in a little bit more depth so you understand why even these matter. Let's look at predefined data models first in a little bit more depth. So package data models, also known as predefined data models, are standardized reusable data models or reusable data models designed to address common business scenarios across various industries. These models provide a starting point for database design and can be customized to fit specific organizational needs. Here are three examples of packaged data models that I would like to share with you so you understand in more depth. The first example, I have handpicked these examples, three in specific, so you understand how industry is giving us packaged data models. First one is Salesforce data model. Salesforce is a huge company. It's a leading customer relationship management platform or CRM platform, provides a packaged data model designed to manage sales, marketing, and customer service process. The Salesforce data models include predefined entities and relationships that cater to common business scenarios. The key entities in a Salesforce data model are account, contact, opportunity, lead, and the case. Account has account ID, account name, industry, annual revenue. Contact has contact ID, first name, last name, email, phone. Opportunity has opportunity ID, account ID, close date, stage, amount. Lead has lead ID, first name, last name, company, email, phone number. Case has case ID, contact ID, subject, description, status. Predefined relationships in the Salesforce model are an account can have several contacts or multiple contacts. An account can have multiple opportunities. A lead can be converted into an account, contact, and opportunity simultaneously. A contact can have multiple cases. The Salesforce data model helps organizations to quickly set up and manage their CRM processes, reducing the time and effort required to create a custom data model from scratch. The next one I have handpicked for you to understand is Microsoft Dynamics 365 data model. Microsoft Dynamics 365 is a suite of business applications that include predefined data models for various business processes such as sales, marketing, customer service, finance, and operations. The Dynamics 365 data model provides a comprehensive set of entities and relationships to address common business scenarios. The key entities in the Dynamics 365 data model focusing on sales and customer service, as we have discussed Salesforce earlier, has an account, contact, opportunity, lead, and case, where the features remains the same. It starts with account ID, contact ID, opportunity ID, lead ID, and case ID. Predefined relationships is exactly the same as Salesforce. An account can have multiple contacts. An account can be multiple opportunities. A lead can be qualified into account, contact, and opportunity. A contact can have multiple cases. So the Dynamics 365 data model enables organizations to implement standardized business processes quickly and efficiently with a flexibility to customize data models as needed. The same is SAP or Simple Application Processes, ERP, technically ERP means Enterprise Resource Planning Software, is a comprehensive software solution that provides predefined data models for various business processes, including finance, procurement, sales, production, and human resources. The SAP ERP data model includes a wide range of entities and relationships designed to support complex business scenarios. So again, the SAP has the same customer, material, sales order item, delivery as you have seen at Pine Valley. In that case, a customer can place multiple sales orders. A sales order can have multiple sales order items. A sales order item is associated with the material. A sales order can have multiple deliveries. The SAP ERP data model helps organizations to streamline their business processes and integrate various functional areas, providing a solid foundation for enterprise-wide data management. These examples illustrate how packaged data models can be used to accelerate the implementation of common business processes, reduce the complexity of database design, and provide a standardized framework for data management. By leveraging predefined data models, organizations can focus on customizing and extending the data models to meet their specific needs rather than starting from scratch. So now let's look into universal data models with few examples. Universal data models are designed to be industry agnostic and provide a standardized, comprehensive framework for representing common data entities and relationships across various domains. These models aim to promote data interoperability, simplify data integration, and facilitate data sharing among different systems and organizations. Here are three examples of universal data models, as usually I take three different distinct examples to help you. The first one can be DCMI metadata terms, also known as Dublin Core Metadata Initiative. The Dublin Core Metadata Initiative, or DCMI, has developed a universal data model for describing resources such as documents, images, videos, and datasets. The DCMI data term model provides a standardized set of properties and classes that can be used to create inoperable or interoperable metadata records. The key entities or classes in the DCMI metadata term model are resources or resource, agent, location, period. A resource is technically URI, title, description, creator, and data. I would strongly suggest you to take notes because the exams would not come from anywhere but the taught material, and these will come in the examination for you to look into and answer. So let me repeat, DCMI metadata terms model have resource, that is URI, title, unique resource identifier is URI, the title of the resource, the description of the resource, the creator of the resource, and date when the resource has been initiated. Agent has a name and identifier and a role. Location has a name, identifier, and geometry, where exactly that location is. It's on the 10th floor, 11th floor, or something like that. Period. A resource has a period. Name, start date, end date. The key attributes or properties in the DCMI metadata term model are DC, a name given to the resource, an entity primarily responsible for making the resource, the topic of the resource, an account of the resource, a point or period of time associated with an event in the life cycle of the resource. The DCMI metadata terms model enable consistent and interoperable description of resources across various domains. promoting better data discovery, sharing, and integration. So there is another one, is called schema.org. Schema.org is a collaborative initiative aimed at creating and maintaining universal data model for structured data markup on the internet. This model provides standardized vocabulary for describing people, places, things, and relationships between them. Schema.org is widely used for search engine optimization or SEO and improving data interoperability on the web. Why this is important for you to learn? Now that's a good question, because this will allow you to go and learn more on SEO or search engine optimization that by itself can be a startup. The key entities or the types in the schema.org model are a person, an organization, a place, an event, and a product. Person has a name, given name, family name, email address. Organization has a name, legal name of the entity, which is organization, URL or Uniform Resource Locator, address, contact point. A place has name, address, and a geolocation. Event has a name, start date, end date, location, and organizer. Product has a name, an SKU, description, brand, and offers. The key attributes in schema.org model are name, description, URL, address, and start date. Name is the name of the item. Description, the description of the item. URL is the uniform resource locator of the item, where it is. Address, the physical address of the item, and start date, the start date and time of the item, that is ISO, International Standard Organization, Standard 8601 data format. The schema.org helps to create shared vocabulary for structured data markup, enabling better data understanding, exchange, and integration across the web. So hopefully this has given you some in-depth understanding what these things are. I would suggest you to write something in your submission in the assignment as an added. What is FIBO? FIBO, Financial Industry Business Ontology. Financial Industry Business Ontology. As an individual, I would like to receive an email from you that what do you think where the FIBO is applicable as universal data model developed by Enterprise Data Management Council, which is EDMC. And that's your assignment that you can share with me via email. And I'm looking forward to an individual email from you that will be your class participation in this case. Advantages of packaged data models. Use proven model components, as I discussed about Salesforce and Dynamics 365. Save time and cost, so you do not have to redo or recreate the wheel. Less likelihood of data model errors, because since you are not the one responsible who designed that, and these are proven models, you will be able to work with them without any hassles. Easier to evolve and modify over time, so you modify your internal structure of organization to work with these. Aid in requirements determination. Easier to read. Supertype, subtype hierarchies. Promote reuse of the packaged models. Many-to-many relationships enhance model flexibility. Vendor supplied data model fosters integration with vendor applications. Vendor would be SAP. Vendor would be schema.org. Vendor would be the Microsoft Dynamics. Vendor would be Oracle. Vendor would be AWS with the Redshift and Cognos. It can be Google, Bigtable, BigQuery, and all that. Universal models support inter-organizational systems, and this will allow you to understand this in more depth when you are going to actually create databases in upcoming lectures. Figure 3.15 is a party, party role, and role type in a universal data model, you can imagine the entity cluster diagram to be a bird's eye view model. The modeler can then drill down to see detailed view of individual clusters. Basic party universal data model has packaged data models are generic models that can be customized for a particular organization's business rules. A party role from date through date, a person role, person can be employee and have a contact. Organizational role, organization can be a supplier and can have many units such as departments. A customer is associated with all of that, and party can have a party ID, and that party can be a person, can be an organization. This is not a party to come and enjoy your time. It's more of somebody who's participating in some sort of role type. In this case, a customer can be a person, a management individual can be a person, and an organization that can be a manufacturer or that can be a buyer. So here we see an alternative notion or notation for supertype subtype representation. Entity relationship and enhanced entity relationship model have various ways that they can be represented in diagrams, but conceptually they are all pretty similar. So I would suggest you this to read the provided material in more depth so you understand where we stand and how we are going to learn these things, because these are real deal. Database is not going to go anywhere. It does not matter how artificial intelligence comes in what way, responsible AI, ethical AI, emergent AI, or any other AI. If there is no database and there is no data, AI can't do anything. It's exactly like if you know how to ride a bicycle and you don't have a bicycle, it technically, you have a skill, you cannot use it, but you know how to ride a bicycle and you can go from point A to point B if you have a bicycle. But when you'll walk, it'll take some time. So that's how we deal with all these things individually. I hope this lecture has given you some decent understanding. Why I always suggest in my lecture for you to concentrate and take some notes and ask all the questions that you have accumulated while the lecture was being played. So this allows you to have an idea, a vision that how the work has been conducted in the industry on an overall basis. So again, the copyright, please make sure that this work is protected by United States copyright laws and is provided solely for the use of instructors in teaching their courses and assessing student learning. Dissemination or sale of any part of this work, including the World Wide Web, will destroy the integrity. So that's why these lectures are not being available on the internet. And please do not share that, because in the end of the day, whoever shares these without the permission of the Pearson can have a legal liability to face the consequences. So let's summarize whatever we have discussed, and we'll close the lecture and we'll take a 5 to 7 minutes break, and then we'll get started. So here's the summary. So since we have started learning database management systems, the fundamentals, when we are dealing with any data models, whether they are packaged or universal, it doesn't matter. These serve crucial roles in streamlining data management and enhancing data interoperability. The data models are particularly useful for organizations looking to quickly set up and manage specific business processes, as they offer predefined entities and relationships that can be readily implemented and customized. So I suggest you to carry on learning these things by reading the prescribed textbook, because that takes you on a journey with several examples added in terms of learning whether these are packaged or universal data models or any other data models. These are standardized. They allow you to have a reusable frameworks for representing common data entities and relationships, catering to various industries and domains, whether you're a manufacturer, you are a transport manager or transportation company owner, whether you are a reseller, whether you are conducting an SEO, search engine optimization. You can always use Salesforce, Microsoft Dynamics 365, the SAP ERP or Oracle suite, as it's used in several organizations, the Blackboard, the Canvas, the other learning management systems. They all have databases in incorporated within. So we close this lecture and we'll get back in the class in less than 5 to 7 minutes. So go refresh yourself. And if you have taken down the questions, I would suggest you to ask those questions once you come back from the break. Happy learning.